All right. So has it started? Not yet. Yeah. So the recording has started now. Yeah. So we had discussed this interesting M-phi curve, which is moment curvature curve, and you may recall that in a member under flexure, if it is a symmetric cross section, then both extreme fibers, the top extreme fiber and the bottom extreme fiber, if this is the cross member, the top extreme fiber as well as the bottom extreme fiber, both of them. One second. Both of them would, so if this is the member, so the top extreme fiber here, the top extreme fiber here, sorry, trying to get my pen to work. Yeah. So the top extreme fiber here and the bottom extreme fiber here, they both yield at the same time under pure flexure. And when that happens, that is when you will have one limiting moment that you can call My. Correct? And subsequently, as you keep increasing the curvature, more and more fibers start to yield, and then you will end up with the situation where the entire cross section has yielded. Half of it has yielded in tension, that is, let's say, bottom part, and half of it has yielded in compression, that is the top part. And then you will end up with something beyond E. So what you see here is this point where the entire cross section has yielded, and the difference between My here and MP here, this difference is basically the reserve capacity beyond My, beyond the first yield. Yeah, and that reserve capacity can be utilized only if the cross section has certain attributes, certain qualities. Yeah, in fact, even My may or may not be utilized fully, depending on what attributes does it have, the cross section has, and which are those attributes. We had discussed those in details. That attribute that I'm talking about here is the susceptibility against local buckling. So if the cross section is susceptible against local buckling, then you may not be able to utilize My a little bit more than My all the way to MP, depending on how susceptible the cross section is against local buckling. Okay. So the limit state point of view, if you think of a flexural member undergoing flexural failure, the limit state would have been yielding or plasticization. So yielding means extreme fiber yielding versus plasticization of the entire cross section. Condition 2, or depending on the condition, that it should not undergo local buckling. Correct? So basically, local buckling as such is not a limit state as far as design provisions of IS 800 are concerned. If you go to IS 801, there is a limit state of local buckling as well. That means there are formulae given for designing a member against local buckling. However, in case of IS 800, you don't have to use any formulae to calculate the capacity against local buckling. That is not possible. It does not do that. You can prevent local buckling before yielding if you follow certain guidelines, and those guidelines are quite straightforward. Let me try to go to those here. So depending on what is the here. So table 2 of IS 800, we had discussed this table, and there were several classifications of the cross sections depending on the B by T values. Different B by T values. So this is a long table. Depending on how thick the cross-sectional elements are, for example, if you have a, let me get it. So if I have a beam, sorry, my drawing is turning out very, very poor. Okay. So if I have a beam, the ratio between the thickness of the flange versus the width of the flange. So here we will use half of the width and we will use the thickness. So width versus thickness, that ratio, if that ratio is large, then your member is more towards slender or semi-compact. And if the thickness is low, width to thickness ratio is low, then your member is more likely to be plastic or compact? Correct. So this was the way to handle local buckling, the possibility of local buckling. Now coming to the design provision. So as far as the limit state of yielding was concerned, the limit state of yielding, okay, and local buckling possibility is inbuilt implicitly, not explicitly, implicitly, because you have to make sure that the cross section is at least semi-compact. So you may have two types of cross sections as per IS 800. Either you may have a semi-compact cross section, or you may have a compact or plastic cross section. So if the cross section is compact or plastic, then the moment capacity MD is equal to ZP Fy divided by gamma M0. However, if your cross section is semi-compact, so this is for plastic and compact. If the cross section is semi-compact, then your capacity is ZE Fy divided by gamma M0. This is for semi-compact. Sorry, this is for semi-compact. All right. So this beta B is just basically doing this thing. This is in a simpler way. What I've written here is a simpler way of writing the same formula. Okay. On top of that, there was one more condition that is added in this provision. If you go to clause 8.2.1.2, let me try to go to that clause 8212. Can you see my screen? Can you see IS 800 8212 clause number? Maybe somebody can unmute their camera, unmute their microphone and tell me. You can see it, right? Somebody has, yeah. Okay. So in this 8212, here is that expression beta B ZP Fy by gamma M0 that we have just seen. And in addition to that, these two lines here, what you see, can I highlight it? Highlight you. MD shall be less than 1.2 times this in case of simply supported, and 1.5 times this in case of cantilever beam. So what it is saying here is MD should be less than 1.2 times the ZE Fy by gamma M0. So going back to previous equation, in the previous equation, what it was saying that if the cross section is semi-compact, then the capacity is ZE Fy by gamma M0. But if it is plastic or compact, then the capacity is ZP Fy by gamma M0. So ZP can be used, and ZP will be greater than ZE, obviously. So ZP can be used. However, if the ZP is much higher than ZE, what is ZP? Plastic section modulus, and ZE is elastic section modulus, or the section modulus corresponding to first yield. Okay, so of course ZP will be larger than ZE, but if ZP is much greater than ZE, in that case you cannot use more than 20% of ZE here, and you cannot use more than 50% of ZE here if the beam is simply supported beam and if the beam is cantilever beam. This is where we had, I think, stopped the discussion last time, and I had asked you to think about it. Why should this be? Okay, so basically, somebody had pointed out in the previous lecture that yes, it is to prevent, or it is to limit the amount of damage the beam can undergo. What is damage? Any kind of plasticization is damage. So the thing is that under extreme load, design load rather, under design load, the beam is going to plasticize, and that is why we have designed it as per this equation. Okay, because we are allowing plasticization under the design load. But design load is much higher than the service load, because you might be remembering some load factors that you have to use, right? So when you use the load factors, then your design load are calculated, but design loads are higher than the service loads. Service loads are much lower. So under service loads, you should not have much of plasticization in the beam. And the problem is that if you use a ZP value which is much higher than ZE value. That means under the design load, the cross section will plasticize fully, but there is a chance that under the service load also, it will exceed the stresses corresponding to ZE and it will plasticize. Okay, and the provision wants to prevent the plasticization under service loads. Under service loads, the beam should not have any damage, but under extreme, under the design load, it should be okay. Right? So that's why these factors are brought in, 1.2 and 1.5. So your ZP, if it is more than 1.2 times ZE in a simply supported beam, then you cannot use your ZP. You have to use your ZE times 1.2. That is the limit. Similarly, in a cantilever beam, if your ZP is more than 1.5 times ZE, then you cannot use full ZP. You have to use, you cannot use full ZP. You have to use only 50% more than ZE. Okay. The question arises, why are two separate limits given for different types of boundary conditions? So for the simply supported boundary condition, the limit is given as 20%. For cantilever beam, the limit is given as 50%. Why? Since the two-way communication is not very easy in this presentation, so I think I'll keep going ahead with giving the answers. So this answer is basically, I have tried to find at various places. It is not officially given in any textbook, but this is what my understanding of damage development is, and that is why I'm giving this explanation. Okay, so far I have not been able to find any good explanation for this reason, but this is my understanding, and that's why I'm explaining it this way. So what happens if you have a distributed load in a cantilever beam? How does the bending moment diagram look like? It looks somewhat like this, right? A parabola, correct? Similarly, if the simply supported beam is subjected to a distributed load, uniformly distributed load, the bending moment diagram looks like this. Okay, where is the location of highest bending moment? Here. The variation of bending moment in that neighborhood is very, very gradual, very, very slow, right? So there is a large region that has a very large bending moment, almost uniform bending moment. Whereas in case of cantilever, the region that has large bending moment is very small, because the bending moment starts to drop almost immediately beyond the maximum bending moment location. Yeah. So as a consequence, the portion that is going to undergo damage in a simply supported beam is much larger. So let's say this reaches MP value, right? Plastic moment capacity value. That means a large portion of the beam would be under moment that will be larger than My. Okay. So for example, let me try to get it there. So if let's say this is the MP value, okay, and this is the My value, the point where the yielding first takes place. Sorry. So if you look at the portion that is beyond My, that is more than My, is very, very large. Whereas in this case, if this is the MP value and this is My value, the portion that is undergoing damage is very small. Here, the portion that is undergoing damage is very large. Okay. Because of that, they have set the limit to the ratio of MP versus My as small. Therefore, for simply supported beams, the ratio of MP by My or ZP by ZY, same ratio, right? MP by My is nothing but ZP by ZY. So the ratio of MP by My or ZP by ZY is set as 20% maximum. If it is more than 20%, you cannot use MP. You have to use 1.2 times My. Whereas in this case, you can use up to 50% because the area that is undergoing that damage is smaller in kind of a cantilever. Okay. So this is one important aspect that I wanted to discuss. Can we have some discussions now? Let me see if you guys are able to follow. Can you please, if you have any questions, please unmute yourself and ask the question. If you are following okay, just say going okay, no issue. Otherwise, just type anything that you want to say or comment or ask. Or if you want me to explain something again, you can go back. You can ask me now. So you followed it, right? Whatever I was discussing here. Okay, good. At least if you are saying it's all good. Okay, so I will erase this one. Otherwise, when you get the final slides, it will not be visible. It will be very confusing. Okay, moving forward. Now, there is another issue. So, you may remember we have discussed in quite a bit of detail about the failure criteria for material, right? And there were two failure criteria that we had discussed. One was the Tresca criteria, the other one was the von Mises criteria. And I had mentioned that for metals, both of them can be used, but most of the modern design codes follow von Mises criteria. Okay. So since von Mises criteria says that metals tend to yield in pure shear at what stress level? Anybody remembers what was the stress level when material yields under pure shear? Can somebody type? Under pure shear, at what stress level does the material yield? You can type your answer, please. Somebody, one person. Fy by 2. No, that is not. That is by Tresca criterion. Tresca said that at Fy by 2, material will yield in pure shear. What did von Mises say? Fy by Fy by what? Anybody?
Root 3.
Root 3. Very good. Yeah. So yeah, I think Onkar. It was Onkar, right? Who was it? Yeah. So it is Fy by root 3 at which at that stress level material yields. Now, if you imagine for yielding under pure tension or pure compression, you need Fy stress. But under pure shear, you need only Fy by root 3 stress, right? Now, if you imagine a beam, let's say this is the beam that you can see, I section is there, rectangular section is there, T section is there. So for a beam, let's say of I section, there is axial stresses coming. So this might be, let's say, compression, and this might be tension. The bottom part is in tension. The bottom part is in tension. Sorry, what is it? The bottom part is in tension. The top part is in compression. Okay, and all these fibers all along the web, all along the flange, they are all in these stresses. Okay, so the top part is in compression, and the bottom part likewise is in tension. Okay. In addition to that, more often than not, you would have a beam. Whenever you have a beam and you have flexure, you would also have a shear along with that. For example, if I have a beam and I have a load applied on that beam, so I can ask you to calculate the shear force diagram, which will look like this, and I can ask you to draw the bending moment diagram, which will look like this. Correct? So this is the shear force diagram. This is the bending moment diagram. Now, at any given point, let's say I look at this particular point. Okay, at this particular location, there is a certain shear value, shear force, and there is a certain bending moment. Bending moment is carried as I have shown you here. Bending moment will be resisted by these axial stresses. But how is the shear force resisted? The shear force will be resisted. One second. The shear force will be resisted if, let's say, this is one cross section, as this force. So stresses will be acting like this. That's how the shear force will be resisted. If I can draw, if I look at the cross section in the different direction, so this is one part of the beam and this is different other part of the beam, what you will have is, here you would have forces going this way, and here you would have forces going this way. Correct? And if I look at one of the cross sections, if I look at this cross section, this is how it will be. Yeah. Similarly, in the other cross section, all these forces will be going upward. Correct. Now, if you see that the web was carrying either the web or the flange, both. So the flange is also carrying some shear stresses, and also it was carrying some axial stresses. Axial stresses were coming from the bending moment, axial stresses, and the shear stresses are coming from the shear force. Right. The question is, we have so far discussed the failure of a member or yielding of the member under pure flexure. But what happens when there is shear stress also acting? Right. So when the shear stress is also acting, then we have to think of the combined effect of the shear stress and axial stress or longitudinal stress, and the combination of them will lead to yielding of the member sooner. So we may not be able to utilize the full moment capacity of the member. You understand that? Shear will start to interfere with the moment capacity of the member, and it will reduce the moment capacity. Okay. How does the shear stress vary in the cross section? So if I take a rectangular section, then these kind of shear stresses will be acting. Everywhere. Yeah, I'm just showing a few arrows, but it basically means everywhere. So everywhere there will be small shear stress, and the shear stress will vary from top to bottom and will follow this profile, this parabolic profile. Okay, it can be derived. I'm not deriving it here. So it will follow this parabolic profile. The shear stress will be maximum right at the centroid, there where the neutral axis is, and it will be smallest at the extreme edges. If you have an I section, then you can see that the shear stresses will have a jump. So it will be almost like a parabolic profile, like in the previous case, except now you have this parabolic profile, but there is a jump, and then it follows the parabolic profile. There is a drop, and then parabolic profile. That jump corresponds to the change in thickness of the or width of the member at these locations. Correct? As a consequence, you can see most of the shear stress actually acts where the web is. So the web part contributes the maximum of the shear force demand. So if you apply any particular shear force, let's say at this location there is certain shear force demand. If you just take the total cross section of the web and multiply, or sorry, take that shear force, divide with the total cross section of the web, you will get the average stress. So what we typically do is, we take that shear force demand, we do that V divided by area of the web, and that gives a tau value, and that tau value we take as the average tau everywhere. Okay, and we disregard this parabolic distribution in this area. We disregard this parabolic distribution. We assume it to be almost uniform, and we take that as a tau value, tau demand. Okay, so and so from here we know that the shear stresses are going to be taken mostly by the web, but most of the contribution towards bending moment comes not from the web. It comes mostly from the flanges, because flanges are located farthest away from the neutral axis. Therefore, flanges will contribute the most in the bending moment. Okay. So if what may happen, let's say I have a beam, and that beam is subjected to certain shear force demand, just like this beam. This beam is subjected to a shear force demand, and the shear force demand is so much at a particular cross section that the capacity under shear, this tau under shear, has reached. Anybody has a question? No. Okay. So the shear force demand is so much that the web has almost yielded. If my tau is so high that it is almost equal to Fy by √3, that is the limit for yielding. In that case, I cannot take the contribution that is coming from the web, any additional contribution from the web for bending moment resistance, because the web has already yielded. Now it cannot offer any more resistance towards the bending moment. Correct? That means it cannot take any additional axial stresses. It has already yielded in shear. However, the flanges still have very high stress capacity left, reserve stress left, because when the web was yielding, the flanges were at a very low stress level. And as a consequence, flanges can still carry a lot of axial stresses, which will contribute towards bending moment resistance. Okay. So the code handles this philosophy in the following manner. Here is what the code says. The code says that let's say you first you calculate what is the VD value. VD is the design capacity in shear. And as I have explained here, you know your shear stress capacity, right? Which is equal to Fy by root 3, 0.57 Fy. Okay, sorry. Fy by root 3. So your tau is equal to Fy by root 3. And you know how much area AW is available. Correct? So tau multiplied by tau limit multiplied by AW, this will give you VD, design, and plus the moment, the factor of safety will give you the VD value, the design shear capacity value. So if your shear demand has increased 60% of the shear capacity value, if your shear demand has increased beyond 60% of the shear capacity value, that means that your the capacity of the web to contribute towards flexure is diminishing. As long as your shear demand is less than 60% of VD, your web and flange can be considered as fully contributing towards flexure, and you don't have to worry about shear or shear interfering with moment capacity. So your moment capacity will be unchanged, unaffected by shear if your V is less than 60% of VD. Okay. Shear demand is less than 60% of shear capacity, then your moment capacity will be unaffected. However, if your V is greater than or equal to 60% of VD, then it will be affected by the shear demand. In that case, what you have to do is, if you can see this curve here. So in this curve, I have plotted V versus VD. So I have plotted V versus VD against M capacity. So what the code says is that when the V value reaches VD, that is this point. When V reaches VD, that is V is equal to VD, or V divided by VD is equal to 1. So when V reaches VD, you are at 1. At that time, your web has completely yielded in shear. So we cannot take contribution of the web towards flexure. What we can do? We can take the contribution only from the flanges, because flanges are at a very low stress level. So what you can do is you can take MFD. What is MFD? MFD is the moment capacity of the portion that does not carry shear. Which portion that does not carry much shear? Flanges. That is flanges. So you take the moment capacity coming only from the flanges. So when you do the calculation for moment capacity, you ignore the presence of web. You assume that web does not exist. Take only the flanges and calculate the moment capacity from the flanges, and that will be your MFD value, and that will be your capacity. If the shear demand is so high that your V has become equal to VD. However, if your V is 60% of VD at this level, okay, if V is less than, or sorry, more than 60% of VD, then you have to consider a drop in the capacity, and the formula that you have to follow is this one. So there is a beta factor that you can substitute here, that is V divided by VD minus 1, 2 times V divided by VD minus 1, and that varies like this parabolically. Okay, so you assume this formula, which is basically an empirical formula, and as the shear capacity keeps increasing, so if the shear is equal to 0.6 times VD, so you got 2 multiplied by 0.6, that is 1.2 minus 1, that is 0.2 squared, that is 0.04 times this one. So there will be some reduction in the moment capacity. Okay. So this is this provision. In addition to that, you cannot exceed more than 20% of the ZE value. Again, this is to limit the amount of damage. Okay. Is this part clear, or is there any questions here? This is a very, very, very critical part of this discussion. So I want all of you to be able to follow it very clearly. Please ask me if you have any questions. No questions? Okay. I'm kind of feeling that this is a bit complex part, so I'm kind of not 100% sure that everybody has completely followed it. Anyway, I'll take your word. If you have any questions, you can always come back to me. You can write an email to me, or you can discuss in the next class. Okay, so this is the basic design philosophy that we follow. I'll just summarize again. So when you are designing for the moment capacity, first you need to check what is the shear demand. So if the shear demand is less than 60% of the shear capacity, then the moment capacity is not affected by the presence of the shear force, and you can design it for the full moment capacity, whatever we have done before. However, if the shear demand is more than 60% of the shear capacity, then you have to take a certain portion of the contribution from the web and full contribution from the flange. If the shear demand is equal to full shear capacity, right? So if V is equal to VB fully, then you completely ignore the contribution from the web and take only from the contribution from the flanges. Yeah. And anything in between, you need to interpolate using this formula, beta formula. Yeah. Okay. All right. So now we have discussed plasticization limit state or yielding limit state for beams. Okay. So we have discussed how to avoid local buckling so that we can utilize the limit state of yielding. We have discussed how to account for combined shear and flexural effect. Now we will get to the part that really makes steel construction or steel structural design interesting. Okay, so for whatever you have seen was relatively easy. All of this was coming directly from your mechanics 101 class, whichever that class was, mechanics 1 class, I think. So far whatever you have utilized is not much advanced from what you have studied before. But the new part that we are going to discuss is slightly more involved. Okay, so as you might be familiar that whenever we deal with steel structures, instability is a major concern. Why is it a major concern? Because steel, in comparison to other construction materials like timber or concrete or other materials that are used, masonry, steel is a very high strength material. So if you compare, a high elastic modulus material, that is, its elastic modulus is relatively the steel members, when you make steel members, they turn out to be very slender, and because of the slenderness of these members, they are also susceptible to buckling. Okay, so most of the structural members which are made in steel, they are always susceptible to buckling, and you have to always keep an eye to monitor that it should not undergo buckling. So there is one limit state of buckling also in beams. You are familiar with the buckling limit state for columns, right? For a column, if I had a column, let's say, I'm just repeating some obvious things. So if I had a column, and you applied an axial load P, the elastic buckling equation for this perfectly straight column was pi square EI divided by KL squared. Correct? Where this is the length L and K depends on the boundary conditions. You are all familiar with it. That was a possibility for a column, and that was a possibility in a column because wherever you have compression, there is a possibility of buckling, and a column is obviously completely in compression. In a beam also, if you think about it, half of the cross section of the beam, so if I have a beam and it is subjected to bending moment, there is some bending moment acting on this beam. If I take half of some portion of this beam, I can see that there is a net compression acting here and there is a net tension acting here, isn't it? So the top part will be under compression. The top part will be under compression, the bottom part will be under tension. So the part that is under compression has a susceptibility for buckling. correct? And that is an actual limit state that we have to be careful about, and we need to design members for. Okay. So there is a type of buckling which is known as lateral torsional buckling. Yeah. In a typical beam, as is shown in the first figure here, this is a I-section beam. You have top part that is in compression. You may have bottom part that is in tension. That is, if it is positive bending. If it is negative bending, then you will have a bottom part in compression and top part in tension. Either way. So one half of it is in compression, one half is in tension. In such kind of a condition, the part that is in compression can undergo buckling, right? And that is movement, right? So if this part wants to move away from this position in order to undergo buckling, it can go this way or it can go this way. It can go vertically down, it can go horizontally. If it goes vertically down, that will lead to the entire cross-section moving. That is not really buckling, that is regular bending. However, if it moves laterally away, like so, like in the third figure, that is a real possibility. So the top part that wants to buckle will move more, but the bottom part that is in tension doesn't want to buckle will move less, or it will try to prevent the movement of the top part. So basically what you will end up is a slight lateral movement. What you will end up with is a lateral movement and also a rotation. Why rotation? Because one part wants to move more than the other part. That's why rotation. And as a net, you will have some lateral movement. That is lateral movement. So that's why these two words come: lateral torsional buckling, because there is a lateral movement and there is a twisting, torsion going on. Yeah. So this kind of buckling is called lateral torsional buckling. This is also very similar to the flexural torsional buckling that you might have been taught about in the column section, in the column chapter. Okay, so this kind of a buckling is possible in sections which don't have very high torsional rigidity or which have a low torsional rigidity. Okay, and also flexural rigidity about y-y axis. So if the cross section has a very high flexural rigidity in the y-y axis, then this is not possible. This kind of a buckling can be prevented. For example, if I have an I section like this, it has a, and then in the axial direction it is going this way. Okay, and then this is one end, the other end also is supported, and then the load is applied along the longitudinal axis. In this case, you will not have a lateral torsional buckling because it has a very high rigidity in the lateral direction. But this beam has a low rigidity, low stiffness in the lateral direction, and it is susceptible to undergo lateral torsional buckling. Okay, so lateral torsional buckling looks like this. What I will do is, there are two. It's a combination of two deformations, that is lateral deformation and rotation. That's how typically it looks like. What I'll do is I'll show you some videos, and from here you can try to understand. So here is a simply supported beam. This one is a simply supported beam. This is a simply supported beam. At the middle point, at the midspan, a vertically downward load is applied, and this is an I section. This is a real experiment. What you can see here is I can't play the video again. Sorry. Yeah. So action load is applied on this beam. Yeah. So here, what you can see is this is the action load being applied here, right here. Can you see the mouse? Can you see the pointer? I hope you can. Oh, I just saw some messages. Maybe in the next class I will discuss this part. Okay. Let me pause this one. So in this particular beam, you can see that this action load is being applied to push it downward. And as the there are two plots here. The first plot is showing force versus vertical displacement. So as more and more force is applied, vertical displacement is increasing. For example, at this instant, 90 kilonewton load is applied, and the vertical displacement is approximately 7 to 8 millimeter. In this case, it is plotting force versus horizontal displacement. So as the force is applied, there is no horizontal displacement. You can see that the graph is going almost vertically upward. That means there is no horizontal displacement, right? And you do not expect, you have a beam, you are moving it downward, there is no horizontal displacement. It is only moving downward. Yeah. And you keep applying more and more force, you keep monitoring these plots. So till this point, you can see that vertical displacement has increased to more than 10 millimeter, but horizontal displacement is only about not even 1 millimeter. Okay. We keep pushing it forward. Suddenly, what you notice is that at this point, the vertical displacement starts to increase relatively rapidly. But if you see horizontal displacement, it suddenly shoots up. So far, horizontal displacement was very small in comparison to vertical displacement, but suddenly the horizontal displacement has become more than 20 mm, whereas the vertical displacement is only about 13 mm. And then it keeps growing very rapidly. Yeah. So the plot that you see here, the plot that you see here is a very clear sign of buckling. This is the typical bifurcation kind of a curve. This is the typical elastic plastic or elastic deformation followed by buckling curve. But this is a very clear sign of your bifurcation. Yeah. So that clearly shows, and if you look at the profile of the beam, you can see that the beam has undergone lateral torsion buckling. Isn't it? You can see the beam twisting as well as moving laterally. All right. Okay, so I think I should pause here. I will. There is one more video which I will share this lecture notes again with you. So, or this video recording I will share in the next class. And there are a couple of questions that were asked, but I don't think I'll have time today. This particular question, somebody had asked, why are we using? Can you explain the graph again? And another question was, why is it 60% only? So I'll try to answer. 60%, I don't have an answer to that. It is empirical calculation. Ideally, it should start interfering, shear stress should start interfering with the moment capacity as soon as the shear stress is non-zero. But empirically, they might have seen that up to 60% of the shear capacity, it does not change the moment capacity very significantly, but beyond 60% it does. From pure mechanics point of view, the interference should start coming quite early, but we cannot say for sure because there are many other factors that go into affecting the moment capacity. So sorry, I don't have an exact answer to that. All I can say is that experimentally that has been observed. Explain the graph again. Okay, I'll explain this graph next time again in the next class. For now, I think I have to give you guys to connect with other classes if you have any, and I also have to do something. So I'll stop here. We will try to start the class exactly on time next time onwards. Next time too. Okay. All right. So any other questions if you have, you can come back to me, ask those questions later. Yeah. All right. Thank you guys. I'm stopping the recording and the presentation.